Okay, so 6.3 is called vectors. So we have like a drastic change in topic between 6.2 and 6.3. You're still going to see things like cosine and sine come out in these sections, but in a very different way. A reminder, your test, which is right now scheduled for next Friday, will be all of 6. So 6.1 to 6.5 is how far it goes. It's not too long of a chapter. And the next 3 sections all involve some sort of, the next 2, are vectors. And then in 6.5, we get into something called component form. Well, we'll talk about it when we get there. But you're graphing on an imaginary plane in 6.5, so it's a little different. So 6.3 starts with what is a vector? A vector is basically a line segment because it has 2 endpoints that has direction. So these have length and they have direction. Okay, so it's not just a regular segment. It looks a little bit like a regular segment in that it has 2 endpoints, but it will always have this little arrow, and that arrow is telling you what direction it goes in. It's kind of like slope. Okay. You can name a vector 2 ways. One is with this little arrow over the top of 2 letters. And one is just with a single, and it's usually bolded or italicized lowercase letter. So this vector can be called vector PQ, or it can be called vector V. Again, lowercase, usually bold, but sometimes italicized letter. Okay? What's important about the way that this PQ is named is that the arrow is over the letter in which the arrow points to. So if you remember rays from geometry, a ray had a single endpoint and then it had an arrow on the other side. And the arrow always went over the letter where the arrow is pointing. That's kind of the idea here, except that this is not a ray because it stops. So we can actually find its length, okay? There's 2 parts to it, there are 2 points to it, which is the initial point and the terminal point. Obviously, the arrow points towards the terminal point, so it points away from the initial point. So you're going to do a lot of things with vectors, but one of the things is to draw it, and when you draw a vector, you have to have it have direction. So the arrow always points towards the terminal point. It will either say P is the initial point, Q is the terminal point, or it will give it a name, like this one, where you would see the arrow over the terminal point, and so that's how you would know. The first thing we're going to learn about a vector is how to find its component form. So component form is found by doing the terminal x minus the initial x, and then comma, terminal y minus the initial y. It's very similar to slope, but it looks like it's in coordinate point form. So it's the change in x, comma, change in y. You know where like slope is change in y over change in x. This would be change in x, comma, change in y. And these are not parentheses, okay, for a reason. When you write this, it will be a single number, comma, another number. And those brackets will be there like that. That's how you know the difference between a coordinate point and component form.
So these are brackets?
They have like their little, I actually don't know if you have them on your regular keyboard. They look like brackets, but they're actually supposed to be sharp like that. Just know that they are not the same as this. This is a coordinate point. This is a vector. The second thing we're going to find for a vector is magnitude. Magnitude is the same thing as length. So remember, because they have endpoints, we can find the length. And we find the length by using the distance formula between the 2 points. So the square root of x2 minus x1 in parentheses squared plus y2 minus y1 in parentheses squared. That's if you have the 2 points. So if you're given the initial point and the terminal point, you're going to use the distance formula. If you're given it in vector form, which again has those little brackets, then, and this should actually have 2 bars on it. This should be like this. That's how you show magnitude. Then the magnitude is equal to the square root of a squared plus b squared. So it will already give you the change in x and the change in y. Change in x is like this. Change in y is like this. You just do the square root of x squared plus y squared. A squared plus b squared.
Ms. Chris Buzzer?
Yeah.
Would v also also be an absolute value, or that's just?
No, it's a different, like it's a double absolute value, and that's how you know it's magnitude. So if we're keeping a reference sheet for your test, and I would strongly recommend that you do, 6-1, you want your law of cosine, or your law of sines, you want your angle, area of an ambiguous triangle, an oblique triangle, not ambiguous. 6-2, you want your law of cosines for standard and for the angle. And then your area with S, your Heron's formula. We want to add on magnitude component form for vectors. You're going to add, there's a lot of stuff in here that you can add to it. But if you want to keep a running reference sheet, I would add things. All right, and then equivalent vectors are vectors that have the same magnitude and direction. So in order for for two vectors to be considered to be equivalent or equal, not only do they have to have the same length, but they also have to have the same direction. So both magnitude and direction. All right, so first example says to show that U is equal to V. So we just said in order to show that these are congruent, they have to have the same magnitude and direction. So these actually, this is so hard to draw on PowerPoint, but these would have endpoints here. So if I want to find, let's start with U. If I want to find the magnitude of U, magnitude again is that double absolute value. I'm going to find the distance formula, or the change in x comma the change in y. So because this starts at 0, 0, my change in x and change in y is actually 2, 3. But let's just say we don't see that. I would do the square root of, now the terminal one is here, right? This is terminal because it's where the arrow points. So it would be the square root of 2 minus 0 squared plus 3 minus 0 squared, square root of 2 squared plus 3 squared, square root of 4 plus 9, square root of 13. That's the magnitude or the length of U. Change in x squared plus the change in y squared.
So the magnitude symbol is just to indicate that it's magnitude, not do anything with it?
Correct. It's not an operation. Correct. The magnitude of V would be the square root of the terminal x minus the terminal, or the initial x, so it would be negative 2 minus a negative 4, which becomes plus 4, squared, plus the terminal y, negative 1 minus a negative 4, plus 4 squared. I get the square root of 2 squared plus 3 squared, 4 plus 9, square root of 13. So there's my magnitude of V. Now they also have to have the same component form. So remember, direction is the same thing as component form. And that's where we do this. So the component form of U is the change in x, which would be 2 minus 0. Change in y, 3 minus 0, 2, 3. That's the component form of U. And then the component form of V, change in x. So negative 2 minus a negative 4 is plus 4. Change in y, negative 1 minus 4, minus a negative 4. 2, 3. So because these two are the same, and these two are the same, we would show that these are equivalent. Now, if I had done the component form first, if I had done these first, then instead of going all out on the distance formula, I could have found the magnitude by doing a squared plus b squared. A is the first one, so 2 squared. B is the second one, 3 squared. And I'd get 4 plus 9, 13. If I had done that with V, I would have taken this, and they are the same numbers. If you have the same component form, you will always have the same magnitude. Not necessarily the other way around. So you can have the same magnitude in different component forms because it could be facing another direction, right? Like if it was a -2, I square it, that negative goes away. So you can have same magnitude, but different component form. Can't have, well, I should say if they have the same component form, it's going to have the same magnitude. So if we had done this in reverse order, once you find the component form, you would have known them to be the same. So you'll have to look at these questions differently depending on what the directions say. If it says find the magnitude in the component form and then determine if they're the same, then obviously you have to find the magnitude in the component form. If it just says to show that they are equivalent, then I can go straight to the component form. And if they are the same, then it means they're going to have the same magnitude. If the component form is different, obviously they wouldn't have the same magnitude. All right, so this one says find the component form and the magnitude of vector V. I'll do A with you, and then you're going to do B by yourself. So now we're just going straight up component form and magnitude. So for A, component form, this is my initial, this is my terminal, so it's 15 minus a -1, comma, 12 minus 5. And I get 16, 7. I know it's component form because it goes in those little brackets. Magnitude, and it doesn't have a name this time, so I'm just going to write magnitude, can be found two ways. One is the distance formula with these two. The other is if I've already done the component form, square root of 16 squared plus 7 squared. So 16 times 16. $256 plus 49 square root of 305. See if that can be reduced. So 5 goes in 61 times. That can't be reduced. So I'm going to keep it as the square root of 305. And there's the component form and the magnitude. So if the magnitude, obviously the magnitude will usually be a square root. You always need to make sure it's simplified. All right, you do B. Find the component form and the magnitude. So component form for -3, -5, and 5, 1 would be 5 minus a -3 becomes 5 plus 3, which is 8. And then 1 minus a -5 becomes 1 plus 5, which is 6. So my component form is 8, 6. And then the magnitude is the square root of a squared plus b squared, or 8 squared plus 6 squared. And I get square root of 100, which is 10. So again, magnitude is your direction. Length is your, component form is your direction. Magnitude is your length. If I was to actually plot this on a coordinate grid, my initial point was -3, -5, so it would be here. And my terminal point is 5, 1, which is here. So if I had, and it would have had an arrow pointing towards the terminal point, okay? wait for it. Alright, so it would look like that. So if I had actually measured it, it would be 10 units. Okay, if I actually could measure it by boxes, which is a little bit weird on a coordinate grid. But the direction is also kind of like your slope. So think about your change in x and your change in y, right? If I had actually counted the slope of this line, I would have gone to the right 1, 2, 3, 4, 5, 6, 7, 8. There's my change in x, and then my y, 1, 2, 3, 4, 5, 6 would be 6. So that's the other way you can verify component form. Okay, again, think component form is sort of like slope, except slope we do change in y over change of x, or rise over run. Component form is going to be like this, where it would be 8, 6. Where it would be change in x and then change in y. Questions so far?
So if we're graphing it, do we need the magnitude, or we can just graph the 2 points and then just need the...
So if you have initial and terminal, then you'd graph it like we just did, where you plot those 2 points and you connect them. You're going to see in a minute, there's times when you won't have a component, when you won't have the initial and the terminal, and then we'll use the magnitude in a different way.
All right, and how do you use the direction? I don't know, like, what does 8, 6 mean? I don't know what that means.
So that's your change in x and then your change in y. So my change in x is 8, so that's like my run. And my change in y is like my rise, which would be 6.
Okay.
It's like a linear slope. It's weird. It's like slope, but it's different order. All right, a scalar multiple, okay, this is a lot of words, for something that just means an increase of length. So a scalar multiple is a number that gets multiplied by the magnitude of a vector, which means I'm increasing its length or I'm shortening its length, okay? So if I look at just this, if this is v, okay? So this is actually way easier to do in Notability because you can like take those little segments and you can duplicate them. But let's just say this is v. Let's say I had actually measured that length. And then I wanted to find 2v. My line is going to have the exact same slope, so it's going to have the same direction, but it's going to be twice as long. So if I had actually measured from the end point to the end point on v, that would be like, I don't know, like say it's here. I would double it to get 2v. So it's exactly twice the length, okay? So if I give you something, like you'll see, I think in the homework, it'll give you like a picture, and it'll say, here's v, find 2v. You literally just want it twice as long, but you want it in the same direction. So you want the same rise and run. If it's half v, then it'd be literally like half of this v should be the same as that. So these don't have to be perfect, like you don't have to take a ruler and measure them, but kind of like an eyeball. But you do want to know that it would be about half that length, okay? If the sign on the front changes direction, so these had positive slope, right? These went up and to the right. If it changes so that it's negative, notice the arrow changes and points the other direction. So this 3 over 2 means my length is what? What's 3 over 2? 1.5. So it would be 1v and then another half v. But instead of the arrow going in the same direction that it normally goes, which was up here, the negative on the front changes its direction.
And will the line always be like that? That the left is lower than the right?
No. Good question. So if v was, like, let's say I have a coordinate point, a coordinate plane. Let me go back. I don't know if you guys from home just heard Maria, but she said, will it always rise to the right and fall to the left? No. So let's say that my v is that, okay, where it now is rising to the left and falling to the right. If I wanted to find 2v, then it's going to go in the same direction, but it's going to be twice as long.
Would that be negative 2?
If the arrow goes this way, it's going to stay the same as the initial one. So because v was positive in the beginning, I would say that that's positive. If it said negative, now I go the other direction. So this, if it's on a coordinate grid, we actually go the opposite direction, like this. That would be negative v. It goes the other direction. Does that make sense? Okay. If it wasn't on a coordinate grid and we're just drawing them next to each other, you could actually draw it just like that. It would be the same next to it, but the arrow just points the other direction. All right, and then these are all the things that we can do with vectors. Well, so far. We can, if we take two vectors, so this is saying this is vector u and vector v, and scalar, which is just a number, has to be a real number. I can add two vectors, I can subtract two vectors, I could multiply a vector times a scalar, and I can change the direction of a vector by changing the sign. So if I'm adding two vectors, I add both x's, I add I add the x1 and the y1, I add the x2 and the y2. And this type of answer is going to be in vector format. So it's going to be in component form format. It's going to stay that way. Same for here. This would be a number, comma, a number at the end. This is going to be a number, comma, a number at the end, but we'll have taken the number on the front and multiplied it in times both. So they will stay separate. They will stay in component form. You'll just add the two first terms and add the two second terms, or subtract the two first and subtract the two second, or distribute in the scalar. So if there was a number like 2 on the front of a component form, I'm going to distribute it in. And then the negative can either be inside with the v like that, or I can use that distributive property to take the negative out, and it would be the same thing. So the negative changes its direction. All right, and then sketching it. So we just talked about this for a little bit. But if you are given the component form, so if it said U1 and U2, it's not an initial and a terminal, it's its overall component form, then U1 is the change in X and U2 is the change in Y. If they don't give you an initial and a terminal, you start at 0, 0. So if they gave me initial and terminal, I would literally plot initial and terminal and connect them and arrow towards the terminal. But if they don't give you, if no initial or terminal is given, then we always start at 0, 0, and we use the first number as our change in X, and we use the second number as our change in Y. All right, so here we go. Find A, u plus v, B, u minus v, and C, 2u minus 3v. Then sketch each resultant vector. So I'm going to start with A, which is u plus v. I literally take the first two in each one, 2 plus 1, and add them. And then 1 plus 3, the second ones in each one, and add them. And I end up with 3, 4. I'm going to come back and graph these in the end.
In the test, are you going to also make this graph?
Possibly, I haven't made it yet.
Okay.
Probably, because you're going to have to graph in 6.5 anyway, so I'm probably going to do it. Yeah. B is u minus v. So now we're doing the first one minus the second one. And I get 1, negative 2. C is 2u minus 3v. So the first thing we're going to do is distribute the 2 in on the u. So this is like 2 times 2, 1 minus 3 times 1, 3. So I distribute the 2 in here and I end up with 4, 2. I can either distribute the negative and make it plus in between, or I can keep the negative on the outside and subtract. if I distribute the negative, this would be -3, -9. If I kept the negative in between, it would be 3, 9, and then I'd subtract. Either way is fine. You just can't do both. So then I'm adding two components on the left now. 4 plus a -3 and 2 plus a -9, which is 1, -7. On the right, I'm subtracting them. So 4 minus 3 and 2 minus 9, I still get 1, -7. So again, either way you do it is fine. All right, now we're going to go back and graph them. So the first one, the easiest thing to do is to graph the results, but I'm going to show you what would happen if we didn't have that. The easiest thing, again, is to just graph 3, 4. I'd start at 0, 0. I'd go 1, 2, 3, up 1, 2, 3, 4. I draw my line, and I make sure I point my arrow away from the 0, 0. Because that would be the terminal. Now this is if I actually have values here and I can add them together, super easy, add them together and then graph it. Let's say I didn't actually have values here. Let's say it just gave this drawing on a coordinate grid. So it would look something like this. Okay, again, so the beginning I actually have those coordinates, so it's easier to combine them and then do it. If I had that information, I would have done it the first way. But there's going to be times in which you actually won't have coordinate points. You'll just have little segments like this. So the way that you draw this out is you extend these to make almost like a parallelogram. So I'm going to come over to the end of this one, and I'm going to extend my line to be the same as this line. So it looks kind of like that. Same slope, same distance. I'm going to come to the end of the second one, and I'm going to draw the same segment as this first one. So it should be parallel to it, and it should be its same length. Then I do the same thing for the other one. I come to the end here, and I want a segment that is this long and in that direction, like that. And where these 2 points meet would be the terminal, and the 0, 0 would be the initial, and this would be the sum.
Does it matter where the arrow goes?
It does. So the arrow, when you don't have an actual physical initial and terminal point, you always want to point your arrow away from 0, 0. So you're going to see like number 5 in the homework draws it out like this. You've got 2 of your vectors. You're going to extend them out and make like a parallelogram. And where the 2 extensions meet ends up being the terminal point. So this, if I had drawn this out accurately on a coordinate grid, should be the same as that. And again, if I was given the actual component form up here, it's way easier to do it the way that we did it initially. But you may not be given lengths or component forms. You might just be given pictures of vectors. And if you have to add them, you're going to have to do it the way the second method is. So I'll continue to do that with B and C. But just know that if I actually had the lengths like I do for B and C, all I would do is start at 0, 0. Changing X is 1. Changing Y is -2. Connect them and draw the arrow away from the 0, 0. And then B, Draw your lines. This time it's 1, -7. Go to the right one. 1, 2, 3, 4, 5, 6, 7, all the way down here. Initial point. Connect them. Draw the arrow away from the 0, 0. See if they have any negative one time. Sorry, let me just check. Alright, so they're all, so as long as you, again, would be able to draw it after I give you the component form, you're good with tonight's homework, which is where I want you to get. The other way would be to actually draw them out, so that if I gave you a picture without Okay, let's say I gave you this, so we don't know the actual length of those lines, okay? If you are given just a picture to go on, and I ask you to draw U plus V, then I have to extend out parallel to this about the same distance, which would be that. I have to extend out parallel to this about the same distance, and where they meet is the terminal point of what would be the sum. And this is the hardest part for people, okay? And we haven't even gotten to the equations and stuff. But that's what it is. You need to just, and if it had said something like 2u, I would take u, point it in the same direction, make it twice its length. If it said 2u plus v, now I'm doing twice the u and then the v. And it would look like that. So you'd have to do both, okay? So again, for tonight's homework, it's going to give you the component form of it. I want you to work through. I just assigned it all and made it due Thursday. But we got to the point, let me tell you where we got to. We got to the point of number 5. So you should get all the way through 5 today. And then tomorrow we're going to talk about IJ format. And we're going to talk about the angle that would be formed in the direction. So we'll finish these off tomorrow. But you should be at least able to get from 1 to 5. Go ahead, Sai.
So